Hello everyone, this is Team Ethos here to present our project on cyber attacks detection in IoT based smart city network traffic. Our team consists of Rishita, which is me, and Vishal and Sai. First, let me express my gratitude towards Professor Zhang for giving us this opportunity to work on the project. It helped us to explore the datasets and understand the subject in a better way. Let me start my presentation by saying why we chose this project. The whole idea of the Internet of Things is to extend the capability of the Internet beyond computers and smartphones to electronic, mechanical devices, sensors, etc. With the increasing number of use cases of IoT devices, security vulnerabilities have also been increased drastically. Today, IoT devices are used in fire systems, drones, smart homes, healthcare, and they're just a few. You can imagine what a disaster it would be if someone with bad intent gets access to these systems. That's why NIDS, which is Network Intrusion Detection System, is installed, which analyzes all the traffic and detects malicious traffic and helps the organization monitor their cloud, on premise, or hybrid infrastructure. Let me start by introducing the dataset. UNSW-NB dataset consists of raw network packets for generating a hybrid of real, modern, normal activities and synthetic contemporary attack behaviors. The dataset was prepared by the IXIA Perfect Storm tool in the Cyber Range Lab of UNSW, Canberra. This dataset has been categorized into these 9 types of attacks: fuzzers, analysis, backdoors, DOS, exploits, generic, reconnaissance, shellcode, and worms. The goal of the project is to categorize the attack as normal or abnormal, which is a binary classification, or categorize into any one of the above mentioned 9 attack types, that is multi-class classification. So the methods used in our project are data exploration analysis, data engineering, and modeling. Let's begin with the code of our project. In the beginning, we've imported certain libraries which are useful to plot graphs and make mathematical calculations in our project. Some of the examples for the libraries are NumPy, Pandas, and Seaborn. And we've imported other methods from certain other libraries. After that, the initial step of any project which contains dataset is reading and printing out the datasets. So here we've written a code to read in training and testing dataset. So as you can see the output, the number of rows and columns in training dataset and testing dataset are 82,332,45 in training dataset and 175341 rows, 45 columns in testing dataset. After that, we've written a code to see the distribution of data types in the training dataset. The pie chart represents the certain distribution of the data types in the set. As we can see, 66.67% of the data is int64 and 24.44% of the data is float, and rest, that is 8.89%, is string data. The next step we did was to figure out which missing data is present. So it's plotted in the graph, and this is the graph which displays the missing data. Here, all the dark parts is the data that is existing, and the lighter white parts are the data that is missing. As we can see, the only data that is missing is service data. Let's measure the percentage of data that is missing. So here we can see that the number of missing values in service are 475153, which is 57.27%. This is the graph that is plotted in this area. So the null value analysis of the data set concludes that there is 57.27% of missing data. The rest of the project will be explained by our other team members. Thank you.
Hey, hi. So this is Sai Vishal. I also belong to the team of Ethos. Like my friend just explained you on data exploration analysis that we've done and the methods and why we chose the project. Let us jump to the next sections that we have done. So first one would be this one, distribution of service feature. So what we actually did was we kind of have many protocols, right? So like HTTP, FTP, FTP data, SMTP, POP, DNS, SMP, SSL, like that. These are all the internet application layer protocols, and then there are various layers on the application layer, like like on the OS layer. So these protocols belong to different layers, right? So what we did was we plotted a graph which shows the amount of traffic respective to the protocol. So as we see from the plot, we can see protocols like POP3, SNMP, SSL, DHCP, IRC, Radius, and SSH combinedly are less than the 2% of complete the data set. Out of the data set that we have taken, these protocols here are just 2%. Most of the attacks, as we see, are on HTTP. You can see that uh, you know normal HTTP traffic is around 4013, and abnormal HTTP traffic is 4274. And if you see DNS, normal traffic is 3068, but if you see its abnormal traffic, it's 18,299. That is way more higher compared to the abnormal traffic of other protocols. So as we see, we can say that majority attacks, or the majority of abnormal traffic was based on DNS service. Yeah. So if we go here, so what we did was, so we've created categorical and numerical columns in the training data set. So why we have taken numerical columns and categorical columns? Categorical columns is especially for doing one hot encoding and yeah, one hot encoding. And for numerical columns, basically they're graphs where we only apply on numerical columns. So for both of them, we basically have given training data set as the input, and now we've generated it here, right? You can see the output of it. Now what we did was, in order for us to create this plot, we made use of something called a helper function, and where we've actually created function named bar plot, to which we give uh, inputs, various inputs, as you see. And what we do is, here we make use of label, sorry, here we make use of a for loop. uh, with a label, with a variable called x, we loop through the uh, labels. And then what we do is we print the title, and then of what the service is. And as we go down, you can see that we made use of this for loop in order to go through categorical columns. We do the distribution, mm, basing on normal and abnormal traffic, to which we got this graph that is being generated, right? And what we did was, next we did the distribution of state. So as you know, for any protocol, there are states, various states. When they're in, like, when a client and server are communicating, initially they'll be in a in state, and when they finish communicating, they will go to a state called FIN. So like that, we have also distributed the state of each service type, right? So you can see that uh, mm, from this. Oh, so let's go back to the PPT. So if you see, let me, yeah, where is the distribution service? Yeah. So yeah, so ACC, which is this one, RST, reset, and CLO combinedly are negligible compared to the other states. Most states of protocols or the services are in INT and FIN. So now what we do is, after we got to know about this, we did something called binary classification distribution. So here what we did was we called the same function bar plot, where we um, gave training data as in the input and the label, and we check the distribution of label here. And as you can see, there are zero is a normal the green uh, zero represents normal traffic, one represents abnormal traffic. So distribution of label is represented in a binary form here. So which is either normal or abnormal. See, normal traffic is 37 or 37,000. Abnormal traffic is over 45,332. So what we did was, for the same this data, we've created multi-classification distribution, to which we can see that we have uh, attack categories that has given as an argument for the function, same function, bar plot, and we have given the training data set, and now we were able to actually distribute the attack categories. So what you can see is there are two types of traffics, like I said, you normal and abnormal. Here you can see normal is 37,000 as it is plotted in binary classification distribution. Now when we come to abnormal traffic in multi-class distribution and classification distribution, this abnormal traffic is represented in different various forms. They are ranging from reconnaissance, backdoor, denial of service, exploit type attacks, false errors, worms, shellcode attacks, generic attacks, right? So if you go here, so we can see that from the multi-class distribution that we have performed, we can see that out of 9 available types of attacks that were taken into the consideration, worm attacks are very less. Majority, uh, abnormal traffic, if you ask me, are just generic attack types. The next one would be exploits. So from this data we can see that almost 11,132 exploit attacks are exploit type attacks. Next, the fuzzes. The next one you see are denial of service attacks. Then the reconnaissance attacks. So yeah, so from the next part, mm, my teammate Sai will take over. He will briefly explain you the data engineering and the modeling and the results that we get from them. And yeah, so that is it. um, I would like to ask Sai to take over. Thank you.
Hey, hi, I am Sai Kumar Reddy. I'm also part of Team Ethos. My friend explained about the multi-class distribution. Now I'm going to explain about data engineering. So, as a part of data engineering, we will be converting the categorical features into one hot encoding. Like basically we will be converting this columns of proto, state, and service into the integers. That is what called one hot encoding. One hot encoding, like it's nothing but like basically the machine learning algorithm, the model cannot understand the strings. So we will be converting that to integers, like for like we are having different values. For one value we'll be giving it to 0, the another value will be giving it to 1. Like that we will be performing the one hot encoding. So I'll be showing you the code for that. Okay, before going to that, I will also like explain the correlation between the columns. So this plot shows you the correlation between the different columns that were present in the data set. So each row, or sorry, each pixel includes the like the correlation. For example, if you see the D loss and the DB 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 types, so it is light, which means around this we will be having here, which means it is highly correlated. Then we are also removing the uh, not a numbers. So because as a machine learning model cannot understand that, so we will be removing that. Okay, and let me zoom it. So now we are doing the one hot encoding. The basically the attack category, we are having strings, which is used for multi-class distribution. Sorry, multi-class classification. So we, as a machine cannot understand the strings, so we will be doing the one hot encoding, which we'll be converting it to the integers. So basically, what we will be doing is that here we are converting it to the integers, and here we are removing the original column and replacing it with the encoded categorical column. So before coming to binary classification, let me go through different machine learning algorithms that we have used in this project. So coming to the linear regression, it's an machine learning algorithm that will be used to predict the value of a variable based on the value of another variable. So the value that you want to predict is called the dependent variable, and the variable that you want to predict the other variable's value is called the independent variable. So this is a form of, actually it's an analysis that estimates the coefficients of the linear equation involving one or more independent variable that best predict the value of the dependent variable. So basically we will be using the linear regression for the continuous values. Okay, now coming to the logistic regression, it's a process of modeling the probability of a discrete outcome for a given input variable. The most common logistic regression, like it's models a binary outcome, like for something that can take two values such as true or false, 1 and 0, yes or no, like that. We are also having multinomial logistic regression that can model scenarios where there are like more than two possible outcomes. Like if you are getting the outputs as 1, 2, 3 for like that. So logistic regression is a useful analysis method for classification problems where you will be trying to determine if a like new sample fits best into which category. Now coming to the support vector machines. Support vector machines, like we call it as SVM. It's one of the most popular supervised learning algorithms, which is used for classification as well as regression problems. So it is used for it is primarily used for classification problems in machine learning. Even in this project, we are using for classification. So the goal of the SVM algorithm is to create the best line or the decision boundary that can segregate the dimensional space into classes. so that we can easily put the new data point into that correct category in the future. This best decision boundary is called a hyperplane. And the SVM chooses the extreme points or vectors that help in creating the hyperplane. Uh, Basically, SVM will be like it's of two types: linear SVM and non-linear SVM. Linear SVM is used for linearly separable data, which means if a data set can be classified into two classes by using a single straight lines, then such data is termed as linearly separable data, and the classifier is called as uh, linear SVM classifier. Non-linear SVM is used for non-linearly separable data, which means if the data set cannot be classified using a straight line, then such data is called non-linear data, and its classifier is known as non-linear SVM classifier. Now, coming to the decision trees, decision tree is a supervised machine learning algorithm that that is used to categorize or make predictions based on how previous set of question was answered. The model is a form of this model is a form of supervised machine learning, which means the model is trained and tested on a set of data that contains the desired categorization. The decision tree may not always provide a clear-cut answer or a decision. Instead, it may present options so that it will be easy for the data scientist to make decisions on their own. Decision tree, like basically these decision trees imitate human thinking. So it's generally easy for data scientists to interpret the results. A decision tree, like it resembles a tree. So the base of the tree is a root node. From the root node, a flow of uh, a series of decision nodes that depict the decisions will be made. So coming to random forest, random forest is like it's a supervised machine learning algorithm that will be used like majorly used in classification and regression problem. So here also we are using random like for classification. This project it builds the decision trees based on like different samples and take their majority vote for classification and averages in case of regression. One of the most important feature of the random forest algorithm is that like it can handle the data set containing continuous values. Uh, Continuous variables, as in case of regression and categorical variables. It performs better for classification and regression tasks. So coming to boosting is an ensemble learning method that combines a set of weak learners into a strong learner to minimize the training errors. In boosting, a random sample of data is selected, fitted with the model, and then trained sequentially. That is, each model tries to compensate for the weakness of its predecessor. With each iteration, uh, the weak rules from each individual classifier are combined to form one strong prediction rule. Now, basically, like we are having two data sets, like we are creating two final data sets for binary classification and multi-class classification. And for multi-class classification, we are we will be for multi-class classification we will be using for the attack category column. For that, we are having strings, so we, we will use the label encoding for better classification. Let go through the code for that. So now coming to binary classification, here this plot we have displayed a plot that shows the what we say uh, outcome of the label, like for the label column, which is normal and abnormal. Here, like 72.64% of comes under normal, and 27.36 comes under abnormal. And then we are splitting the data, uh, training data and the testing data. So we are splitting in the ratio of 8:2. So which means 80% of the training data and 20% for the testing data. Okay. And then we like we are also we are and then we will be calculating the metrics. For the metrics include accuracy, log loss, F1 score, and ROC score. Okay. And then now we will be training the model for different machine learning algorithms. So first we are fitting the model, and here fitting the model for the linear regression, and we are getting the metrics, and then for the logistic regression, then the support vector missions, and then for the decision trees, and then for the random forest, and then for the boosting algorithm. So after getting these models, we are printing the results. And from the results, we can actually see that we can infer that uh, the decision tree, random forest, and boosting got 100% accuracy, whereas the linear regression, logistic regression, and support vector got somewhat less compared to the other three. Like we can see that the support vector mission is getting the least accuracy, which means it is not well suited for this project. Now coming to multi-class classification. So now we will be here we are displaying the pie chart, which is showing like how many which is showing the different outcomes of the attack categories column. So basically we are having 8 outcomes. So for in that, generic is the one which tops it's of 52.47%. And then, as I mentioned before, these the classes for this is having string data. The attack category column is having a string data, so we will be doing label encoding, that which will be converting the strings to integers. So basically 0 1, like the backdoor will be 0, DOS will be 1, exploits will be 2, and so on. And then we are performing the data split. Here the same we have done before, we are doing here same. We are splitting the data in the ratio of 8:2, which means we are splitting the data like 80% of the data for training and 20% for the testing. And here this is a function for calculating the metrics. Here basically we are having, for binary classification, we are having 4 metrics, but here we are having only 2 metrics, which is accuracy and F1 score. So, and then we will be performing the and we'll be training the models for the different machine learning algorithms. So here we can see we are training the different machine learning. This is the logistic regression, linear regression, logistic regression, support vector mission, decision tree, random forest, and XBGC class for nothing but the boosting algorithm. For all those models, trained models, we are getting the metrics and we will be storing into the models, and then here we are outputting the results. And here if we can see that the For multi-class classification, the linear regression, logistic regression, and support vector machines are like giving very less accuracy, whereas the decision trees, random forest, and boosting algorithms are giving like mm, almost almost near to 100% accuracy, which are 99.8, 99.5, and 99.5, which is a better accuracy. Almost all it is predicting almost all the correct results. So now let's get back to the PPT. So this is what the results we have got from our project. So basically, like for this project, we can suggest that like for even for both the binary and multi-class classification, uh, the the decision trees, random forest, and boosting algorithms are supporting well compared to the other three. So to conclude, from this analysis of the features and modeling the attacks, uh, that can be identified with near perfect score if non-linear models were used either in binary classification or class classification settings. Uh, that's it from and thank you.